Welcome to our deep dive into the fascinating world of metallurgy. In this video, we'll explore the general principles and processes that govern the extraction and use of metals. Metallurgy is the science that deals with the physical and chemical behavior of metallic elements and their mixtures, called alloys. From the occurrence of metals in nature to their extraction, refining, and everyday applications, metallurgy plays a crucial role in modern society. Whether you're curious about how metals are isolated from ores or want to understand the thermodynamic and electrochemical principles behind these processes, you're in the right place. Let's embark on this journey, starting with the basics and building up to advanced concepts, ensuring a comprehensive understanding for everyone. Metals are found in nature in various forms, often combined with other elements in minerals and ores. Some, like gold and platinum, occur in their native state, while others are found as oxides, sulfides, or carbonates. The form in which a metal is found depends on its reactivity and the conditions of the Earth's crust. For example, highly reactive metals such as sodium and potassium are always found as compounds, whereas less reactive metals can be found in their pure form. Understanding the natural occurrence of metals is the first step in the extraction process, as it determines the method used for their isolation. This knowledge also helps in identifying the most efficient and environmentally friendly ways to obtain these valuable resources. Once ores are mined from the earth, they often contain impurities called gangue. The next step is to concentrate the ore, which means increasing the percentage of the desired metal. Various physical and chemical methods are used for this, such as gravity separation, froth flotation, and magnetic separation. The choice of method depends on the nature of the ore and the properties of the metal. Concentration is a crucial step because it reduces the amount of material that needs to be processed in subsequent stages, making extraction more efficient and cost-effective. This process ensures that the maximum amount of metal can be obtained from the ore with minimal waste. After concentration, the next major step is the extraction of crude metal from the concentrated ore. This process varies depending on the type of ore and the metal involved. Common methods include pyrometallurgy, where heat is used to extract metals, and hydrometallurgy, which involves using aqueous solutions. For example, iron is typically extracted from its oxide ores in a blast furnace, while aluminum is obtained from bauxite using electrolysis. The goal is to separate the metal from its chemical combination with other elements, producing a crude, impure form of the metal that can be further refined. Thermodynamics plays a vital role in metallurgy, especially in determining the feasibility of extraction processes. The Gibbs free energy change delta helps predict whether a reaction will occur spontaneously. If delta is negative, the process is thermodynamically favorable. The LM diagram is a useful tool that plots delta for various metal oxides as a function of temperature, helping metallurgists choose the right reducing agent and conditions for extraction. Understanding these principles ensures that energy and resources are used efficiently during metal extraction. LM diagram is a graphical representation that helps in understanding which reducing agents can be used to extract metals from their oxides at different temperatures. Each line on the diagram corresponds to the formation of a particular metal oxide. The lower the line, the more stable the oxide. By comparing the positions of different lines, metallurgists can determine which substances will act as effective reducing agents under specific conditions. This tool is essential for designing efficient extraction processes and minimizing energy consumption. Electrochemistry is another cornerstone of modern metallurgy, especially for metals that are highly reactive and cannot be extracted by chemical reduction. The extraction of aluminum from bauxite and the purification of copper are classic examples. Electrolytic processes use electrical energy to drive non-spontaneous chemical reactions, separating metals from their compounds. The principles of electrolysis, electrode potentials, and cell design are all crucial for efficient and high-purity metal production. The heart of metal extraction are oxidation and reduction reactions. Oxidation involves the loss of electrons, while reduction is the gain of electrons. In metallurgy, the metal ion in the ore is reduced to its metallic form, often using a reducing agent like carbon or hydrogen. Understanding redox reactions is essential for controlling the extraction process and ensuring that the desired metal is obtained efficiently and with minimal impurities. Once crude metal is obtained, it often contains impurities that must be removed to achieve the desired purity. Refining methods include electrolytic refining, zone refining, and distillation. For example, copper is purified by electrolytic refining, where impure copper acts as the anode and pure copper is deposited at the cathode. These processes are designed to selectively remove unwanted elements, resulting in metals that meet industrial standards for use in manufacturing and technology. Let's look at some practical examples to solidify our understanding. For instance, the extraction of iron from hematite involves reduction with carbon in a blast furnace, while aluminum is extracted from bauxite using electrolysis. Each metal requires a tailored approach based on its chemical properties and the nature of its ore. These examples highlight the diversity of techniques used in metallurgy and the importance of selecting the right method for each metal. Aluminium is one of the most widely used metals due to its light weight, strength, and resistance to corrosion. It's found in everything from aircraft and automobiles to kitchen utensils and packaging materials. Its ability to form alloys with other metals makes it even more versatile. The extraction and refining of aluminium have revolutionized industries and contributed to advancements in transportation, construction, and consumer goods. Copper, zinc, and iron are essential metals with diverse applications. Copper is prized for its electrical conductivity and is used extensively in wiring and electronics. Zinc is mainly used for galvanizing iron to prevent rusting, as well as in alloys like brass. Iron in the form of steel is the backbone of construction, transportation, and manufacturing. The unique properties of each metal determine its role in modern technology and infrastructure. Modern metallurgy must also address environmental concerns. Mining and metal extraction can have significant impacts on ecosystems, water resources, and air quality. Advances in green chemistry and sustainable practices are helping to reduce the environmental footprint of metallurgical processes. Recycling metals, using renewable energy, and developing cleaner extraction methods are all part of the ongoing effort to make metallurgy more sustainable for future generations. Let's recap what we've covered so far. Metallurgy involves a series of steps: identifying the occurrence of metals, concentrating ores, extracting and refining metals, and understanding their uses. Thermodynamic and electrochemical principles guide these processes, ensuring efficiency and effectiveness. Real-world examples, such as the extraction of iron and aluminum, illustrate the diversity of techniques. Environmental sustainability is increasingly important, shaping the future of metallurgy. With these foundations, you're well equipped to appreciate the science and technology behind the metals that shape our world. As we look to the future, metallurgy continues to evolve with new materials, advanced extraction techniques, and a greater emphasis on sustainability. Innovations such as nanomaterials, smart alloys, and eco-friendly processes are opening up new possibilities. The integration of data analytics and artificial intelligence is also transforming how metals are discovered, extracted, and utilized. Metallurgy remains a dynamic field, essential for technological progress and environmental stewardship. Thank you for joining us on this exploration. Stay curious and keep learning about the materials that build our world.